Nice.
Perfect.
So the first series of lecture, the first lecture of this series of lectures, is actually an introductory, let's say, lecture of how to use micro and nanotechnology. Sebastian is, I suppose, quite familiar since he works with plasma. So it's about how to use micro and nanotechnology in order to to prepare, let's say, devices or substrates or functional surfaces, which will be the subject of the second lecture. Nowadays, nanotechnology is a common term used in everything, in advertisements, in several claims, and it is supposed to do a magical thing to whatever it is applied on and improve it. This is not the truth. It is okay. It is something that can for sure improve some things or some properties, but it is not a magic spell as it is advertised. So let's start with the definition of nanotechnology. There are several definitions. Nanotechnology is a part of STEM. It is a very interdisciplinary science, which is connected with material science, physics, chemistry, biology, mechanical engineer, chemical engineer, electrical engineering. The most simple definition is that whatever it is between 1 and, let's say, 500 nanometers, at least one dimension of a material, of a thing, of an object that it is between this range can be categorized inside the nano objects. And why everybody uses it as a magic spell? Because at the nanoscale, all the properties, the physical properties, the chemical properties, the material properties change. So we have different behavior when we have a larger object or a smaller object. And this is the main reason that nanotechnology is applied in several fields. But let's see a slide about the sizes. You can see that our hair is around 100 micrometers. The red blood cell is around 5 micrometers in diameter. Bacteria are also in the same range, some micrometers. Viruses are much smaller. And here we have the nanomaterials, which are, let's say, half a micron and below. The ISO definition of nano object is that whatever has at least one dimension in the nanoscale, regardless the other dimensions, because it might be, let's say, a very thin film that is applied over a large area. But even if one of its dimension is below 500, 200, you know, the definition is flexible, can be categorized as nano-object. Nanotechnology is a trend, as we said before, for at least 20 years, I would say, or more. But let's say the capabilities of using things which are very little, very small, has been extensively studied, reviewed, proposed from very long. Richard Feynman had in his talk in 1959 in the American Physical Society conference has pointed out several things. For example, he was wondering why cannot we manipulate materials atoms by atom? Why don't we control the synthesis of molecules in order to have, more unique properties? Why don't we write all the human knowledge on the head of a pin using nanotechnology? And why don't we build machines and instruments that can do these functions? And actually nowadays, after, let's say, 40, 65 years, we can say that, we have the technology there that can provide answers to all these questions pointed out in this conference. Just as the teaser, I have here the Odyssey written on a silicon surface, and it is read using a scanning electron microscope, and so we can fit the entire Odyssey of Homer in a very small chip, in a very small area, like the idea of Feynman of why can't we write the human knowledge on the head of a pin? So we can do it. But why? But what are the differences in the nanoscale? We said before that, material, physical properties change in the nanoscale. One important difference is that the surface area to volume ratio, if we have nano object, increases. Here you can see an example in which if we divide a square rectangle to smaller cubes, you can have an increased surface area instead of having a square of 5 centimeters, let's say. If we divide it and we have multiple squares of 1 centimeter, then the surface area increases exponentially. So this increased surface area compared to the volume is one of the reasons that nanotechnology is important, because by increasing surface area, we can increase interaction between biomolecules, we can tune friction, we can do a lot of things. Another thing that is important is that, for example, the physical properties change. Here we can see that depending on the size of some nanoparticles, we can change the fluorescent color. So this provides us quite a flexibility to produce different colors, to detect different things by having different objects with different sizes. So after this small introduction, in order to understand what is nanotechnology about, let's go to some typical and commonly used methods in order to do patterning on the small scale, on the micro and in the nano scale. The main concept is provided in this slide. So we have a material, a substrate material, and then we use a series of processes which are lithography, etching, deposition, in order to pattern a surface or to create a device. So we will try to talk about most of the commonly used, let's say, processes to do lithography, to do deposition of a material, to do etching. And then in the last part of the presentation, we'll speak about some typical tools we use in order to see these small objects. So the most, let's say, popular method in order to do some patterning is photolithography or optical lithography. And it is actually a process in which a pattern is transferred on a substrate. This substrate, because this methodology started to be used in the integrated systems, typically is a silicon wafer. But nowadays, photolithography is also used to do patterning on different types of materials. So the process starts with the deposition on the substrate of a photosensitive material, which we call photoresist. Up to now, we have two types of photoresists. I will talk about them in the next slide. And then we have a mask, which is transparent in some places and completely non-transparent to other places. So it has the specific pattern that we want to pass to the substrate. Then we expose this photoresist, which has been applied on our substrate through the mask, and we expose certain areas. This expose certain areas, depending on the type of the photoresist, undergo a chemical change and makes them soluble or insoluble to another solution that will be applied at the end. So using this concept, we can create patterns that can be further processed in later steps in order to create patterns on the surface. And this technique is also used in combination with other techniques, for example, in order to do an oxidation, in order to do chemical vapor deposition, a spatterning of the material, in order to etch selectively the substrate, in order to modify the substrate to pattern or to apply a layer that is used as a sacrificial layer. So depending, as I said before, on the photoresist, which is an organic, a polymer-based, let's say, material, which is sensitive to light, depending on the type of the photoresist, if it is a positive tone, then the areas which are exposed, the areas which are exposed to the light will be soluble. If it is a negative tone, the areas that are exposed, which are this, which is the areas above this green rectangle here, will not be soluble and will be insoluble. So depending on the type of the photoresist and the type of mask we use, which is shown here, we can create either this, so gaps here, or gaps in between the patterns of the mask. Then we can use these kind of patterns to deposit, to etch, to create completely different designs, as we'll see later. Photolithography has several types of operation. The most old one was the contact printing. So in this case, the mask was in contact with the substrate. Then they also tested the proximity layer, the proximity type of photolithography, in which a very small gap between the mask, which is shown as the red here, and the substrate was used. And nowadays, in order to increase the productivity of the method, we use the projection type of photolithography. In the contact type of photolithography, we have some serious, let's say, drawbacks, because when you have a mechanical contact between the mask and the substrate, you might scratch the mask or you might scratch the substrate, and these scratches can be important if we speak about small size features. And this is the main reason that the projection photolithography has now passed in the production of the microchips. Because using an objective lens, we try to expose specific parts of the silicon wafer, and then the silicon wafer is moved in order to the entire wafer to be exposed. In this way, we have increased productivity and no, let's say, mechanical failure of the mask or the substrate. In order to further improve the resolution, the productivity, the size, to reduce the size we can produce, people started to work on how to reduce the wavelength. So starting from mercury lamps in 1985, we have gone to deep UV, to laser, to extreme ultraviolet, to E-beam. So we have used almost any type of exposure in order to have smaller features that we can produce. So a first easy to understand thing is that if we reduce the wavelength of the of the light, we can reduce the feature size we can create. So everybody started working with X-ray lithography because you can create really small features. Then another type of lithography was the extreme ultraviolet, in which the wavelength is 13.5 nanometers, which is much shorter than the deep ultraviolet, which was proposed in 2002, and it could be, I don't know why this is happening, and it could lead to even smaller features. Then people also proposed and used focused ion beam lithography. FIBL is similar to other lithographic techniques, but instead of using light, you have an ion beam. The most commonly used ion beam is gallium ions, and on contrary with the other methods, in this method, you could directly mill or modify a substrate without a resist. So it is quite, let's say, versatile to create different things. You don't need the resist, but it is not very, let's say, fast. Another interesting technique is the deep pen lithography, in which you have a very sharp tip in which you can coat some biomolecules or other things, and this can be applied in specific places on a substrate, creating a specific, let's say, pattern of biomolecules. So it is actually a very sharp tip in which we use as a molecular ink, like the pen we had in the past in order to write, but we don't apply ink, but we apply molecules. So you can pattern viruses, bacteria, whatever. So it is also a very nice technique, but again, it is not meant to be used for, let's say, large-scale manufacturing of chips, but rather for more versatile things like small molecules printing, polymer printing, viruses, bacteria, etc. And of course, we have E-beam lithography, in which instead of using light, we use a beam of electrons. The electrons have significantly lower, smaller wavelength, and we don't need a mask in order to create a pattern. So we can write directly on the substrate and on the resist using this electron beam. Of course, this is much slower compared to the projection type of photolithography, but it can create features that can be smaller than 10 nanometers. And of course, we have nano-imprinted lithography, which is a very simple, low-cost, high-throughput method. It has been used in 3 types. In the first one, we have a template, a stamp, in which we pressure and heat on a polymer, on a photoresist in order to create a pattern. In the second type, instead of using pressure and heating, we use UV in order to create the stamp pattern on the photoresist. And of course, we have also molds that we can drop cast a soluble solution on them and then demold them. The third type is also referred as soft lithography and has been extensively used in several microfluidic applications, not on the nanoscale, rather in the microscale and for several MEMS, but it is actually a very easy to use technique in which you have a specific design, then you pour your polymer on top, and then you extract the exact opposite of the stamp you had. Of course, other type of lithographies, and instead of using a mask and a photoresist, one alternative to use colloidal particles. So in this case, you disperse on the substrate a monolayer of colloidal particles. You can find colloidal particles of different sizes, so you can have different types of particles on the surface. And then by modifying the particles, you can either deposit the film or etch the particles and create pillars. Another alternative to this case is the block of polymers. So you have a copolymer deposited on the surface. One polymer has specific selectivity over the other type. So by just etching or using a developer, you can create patterns on the surfaces. So let's compare this first part of lithography techniques. Of course, photolithography and extreme ultraviolet lithography are the fastest types of lithography, and they are commonly used for the production of all the electronic devices we everyday use. Nano-imprint lithography, X-ray lithography, they are also fast, and they can also create large area patterns. Electron beam, on the other hand, electron beam, focused ion beam, deep pen are slower. They have much better resolution, and they are used mostly for prototyping rather than for production. And if we go to cost effectiveness, of course, photolithography and nano-imprint lithography, if we speak about big numbers, using the same stamp are really cheap methods. And of course, as I said before, the resolution and the precision depends on the wavelength we have. So extreme ultraviolet lithography, E-beam lithography have the best performance in terms of resolution and precision. Now that we have created a specific pattern on our photoresist, the next step is, as I said in the beginning, either to deposit the material or to etch on the areas in which the photoresist has been removed. So we'll speak about etching, how to dig inside the materials in the micro and nano scale, and then we will go also to the deposit of materials in between these gaps. Starting with etching, we can see that two main types of etching exist. It is the wet etching and the dry etching. Using these types, we can either have isotropic etching, in which the vertical, let's say, dimension is equivalent to the lateral dimension of etching, and that's why you have this kind of shape form. We have directional etching and anisotropic etching, which is vertical. So either we have, let's say, a somehow lateral dimension of etching, but this is smaller compared to the vertical one, or we have completely vertical etching. Starting with the wet etching techniques, it is, if we have a material like this, we have already patterned using a lithography technique our resist, and we are trying to dig, let's say, inside the substrate. So the removal of this material of the substrate will be done in wet etching using a liquid chemical or an etchant. Okay. A wet etching process is usually isotropic. And it contains three basic steps. The first is the diffusion of the liquid etchant to the structure. So the diffusion here, the reaction between the liquid etchant and the material, okay, and then the diffusion of the byproducts in the reaction from the of the byproducts of the reaction of the liquid with the substrate and the reacted surface. So material removal for wet etching is usually faster, much faster than the dry techniques we'll talk about later. And usually it creates isotropic, let's say, shapes, or some, as we showed before, directional, let's say, anisotropic etching. But you cannot easily take a vertical, a completely vertical profile using wet etching. The parameters that affect the etching rate, how fast this etching occurs, is temperature and, of course, the concentration of the liquid used to do the etching. So, using these techniques, if we want to go using this technique, the wet etching, if we want to go for a directional wet etching, we have to find a correct combination, let's say, of the etchant and the material. So some of the isotropic wet etching agents for silicon is natrium hydroxide, EDP, TMEH, and of course, they do a directional etching resulting in a pyramid-shaped etch pit with a specific angle of 55 degrees, which follows the crystallinity of the silicon wafer. In most of the cases, wet etching results in highly, let's say, isotropic shapes. But as you can see here, if we do the correct combination between the etchant and the material, we can also have some vertical shapes like the ones shown here. In metals, we can find several examples of wet etchants. Here I have the simplest one, in which we have aluminum immersed inside boiled water, creating these nanoscale features that can provide a super hydrophobic behavior, so repulsion of liquids on the surface. This topography is simply created by immersing aluminum substrates in boiling water. Of course, we can use more, let's say, effective etchants like hydrochloric acid in combination with stearic acid in order to do the functionalization. And we can have on aluminum, on zinc, on other metals like copper, different shapes like the ones shown here that afterwards are functionalized with a type of hydrophobic coating and again can provide a really robust superhydrophobic surface. So let's go to the plasma etching technique, which is which is the main, let's say, dry etching technique used in microelectronics, but also in MEMS and in functional surfaces in general. So plasma is the fourth state of nature, and it is actually an ionized gas which has no charge inside a low vacuum, let's say, chamber. Of course, you can also have plasma discharges on atmospheric conditions, but here we speak about vacuum plasma processing. So we have a typical reactor has a gas inlet, we have a shower head, then we have a specific power supply, usually in RF or DC, different type of reactors exist, which create the plasma. And then we can also have a bias voltage in order to increase the velocity of the ions created inside the plasma. Plasma etching has been extensively used in order to create microelectronics, vertical shapes on microelectronics, and in particular, the most effective type of etching is the reactive ion etching, which is a combination of chemical etching and physical etching of the material. In this type of etching, we have ion bombarding from the ions existing inside the plasma, which mechanically etch the material inside the feature we want to etch. And of course, reactive species doing chemical etching on the surface. The combination of this mechanical and chemical etching provides a quite high etching rate, resulting in different shapes, different aspect ratio profiles. Here I'm showing you this method without a mask, because in this technology we use micromasking coming from the material of the reactor. So you can start with a pretty smooth surface of a polymer, and just by doing etching in combination with the mechanism of micromasking coming from the material of the reactor, you can have this nanotexture. But if you combine with a specific particle or pattern size, you can create pillars which can be vertical or can be undercut, like here. So this is the result of a dry plasma, a dry etching technique on a surface which was covered with some specific colloidal particles. The same would happen if instead of particles we used dots or other patterns on a photoresist. And if we go to silicon, to another substrate, again, you can see by tuning the plasma conditions, we can have really high pillars with aspect ratios larger than 80:1. Aspect ratio is referred to the ratio between the height and the width of the pillar. And on the contrary, we can also have larger or smaller, like the ones here, let's say spots on the surface. So tuning the lithography and the etching step, you can create a wide range of different topographies on a surface. And different topographies are, let's say, applicable to different applications. For example, here you could use it for a black silicon application in order to transform light in a photovoltaic application to electricity. But here, the spots could be ideal for biomolecule patterning. So depending on the combination of the techniques, nowadays we have a very powerful, let's say, toolbox of technologies that we can create a wide range of topographies in a wide range of materials. Here is another example in which quite vertical pillars are created again using plasma etching and colloidal lithography. And here is the same pillars created maskless by electron beam lithography and plasma etching. In this application, these pillars were used in order to do electrowetting applications, so reversible to tune, depending on the applied voltage, to tune the wetting properties of a substrate. And now that we have seen how to pattern the resist and how to etch the underlying lay material, let's see what we can do about adding material on specific patterns. So thin film deposition is the process of creating a thin film on a substrate. We can either do it on the entire surface or we can do it on specific features of on specific patterns on the surface, as we said before. In this kind of, let's say, in this kind of methods, it is important to have a very good uniformity of what we have deposited and not to have this kind of fluctuations in the thickness of films. Conformality, so if we have some specific patterns that we want to code homogeneously, we shouldn't have this kind of things, but we should have, regardless if it is vertical or lateral to the coating machine, we should have a very homogeneous coating. And of course, smoothness or roughness. This depends on the application we want to do. In specific applications like the ones shown here, for electronics, optical, or batteries, a very smooth film is required. On the contrary, if we go to the applications that we will talk also in the next lecture about superhydrophobicity, functional surfaces, etc., we might need some roughness. So we should be able to understand what kind of, let's say, method provides the best result depending on what we want to achieve. And here I have listed some of the most commonly used thin film deposition techniques. Of course, the first major, let's say, group of techniques is the evaporated methods. So we have, using the evaporated methods, evaporation can be done by any beam, by ions, by magnetron sputtering, and all these refer to how we deposit the target material on our substrate. Here we use an ion beam in the second one. Here we use an electron beam. Here we use magnetrons. And of course, we have ion beam, which is commonly used in several applications we know, because it provides a very conformal coating and a very smooth one. So we have here, we have the material we want to deposit. Here we have an ion source. And here we have another ion source. So the ions hit on the target, the material we want to deposit, and then it is transferred on our substrate. And of course, the most common evaporative technique is the thermal evaporation, in which we have, let's say, a metal, a polymer, whatever. Nowadays, we can do whatever we want, even low temperature polymer evaporation. And we evaporate the material on a small boat, which is heated, and then these molecules distribute equally on our substrate, which is placed on top of this chamber. And here you can see a real image. Except from the evaporative techniques, we also have CVD, chemical vapor deposition, in which a solid material is deposited from a vapor. So we have a gas going inside a chamber. Here we have the substrate. We heat it in order to accelerate the deposition rate. And we can form a solid material on the surface of our substrate in the form of the thin film, powder, single crystal. Here you can see an example of chemical vapor deposited materials which are also transparent. CVD has been widely used in several applications in sensors, biotechnology, microelectronics, MEMS, microfluidics, whatever. It is a very versatile technique, really easy to do, and really flexible depending on the material. Of course, because you have to heat the substrate, you cannot easily use it to sensitive polymers, and there you can use other techniques. And except from plasma etching, which we mentioned earlier, we also have plasma deposition. So here, a monomer, again, a gas, is introduced inside the chamber, and it is converted by the plasma in reactive let's say, fragments, in radicals, which will recombine to polymers in the gas phase. These polymers are deposited then on top of the surface of the substrate, which is shown here as gray. And you can have really homogeneous films created inside a plasma deposition system. Nowadays, we also have low vacuum and atmospheric pressure deposition systems and a wide range of materials that can be deposited using specific precursors. Here we can see some carbon nanowires grown using plasma deposition inside an ICP reactor. You can see that you can create a film or a porous layer on the material. And now we go to the liquid phase chemical techniques, which are really the most easy to do techniques because they require less equipment and are easier to and cheaper to produce, let's say, a type of material without using specific equipment. So we have electrochemistry, spin coating, deep coating by dipping specific substrates on solutions. We have doctor blades, which is you apply in a solution and then you mechanically remove the excess of it. Another type of mechanical extraction of the excessive film is metering rod. We have slot casting, spray coating, screen printing, inkjet printing, which is also used for printing applications, and of course aerosol. So using these techniques, even with no equipment at all, with simple things, you can really pattern surfaces, you can functionalize surfaces. So these kind of techniques have been widely used to create a wide range of pattern surfaces. I have some examples here. For example, we have here, they just created a super hydrophobic aluminum alloy by spray coating an alcohol solution containing some silica nanoparticles. So they just, like you're painting a wall, they used a spray coating machine with some nanoparticles inside an alcohol solution. They sprayed it, and depending on the spraying cycles and the concentrations, they find the optimum in order to achieve high contact angle and good repulsion against liquids. Then they also tested to several mechanical tests, wetter jets, etc., in order to see how robust is the coating on top of the aluminum. Again, another method. Here they were spraying some silica nanoparticles with octyl 3-ethoxysilane in order to have this kind of topography. So you can easily create coatings on the entire area or on specific spots of the area if you have done a lithography step, and create different types without using any really exotic, let's say, instrument to do the deposition of the material. Another type of material, a chemical method to produce this kind of patterns or pattern or rough surfaces is the salt gel method, which is a chemical method about the synthesis of various nanostructures, especially used for metal oxides and nanoparticles, metal oxide nanoparticles. In this method, we use a molecular precursor, which is the yellow thing you can see in the schematic, and is dissolved in water or alcohol, and it is converted to gel by heating or stirring. Then this precursor can be used using spin coating, template deposition in order to create specific nanowires, electrospinning in order to create fibers, or heat treatment in order to create nanoparticles. So it is a very versatile method to create metal oxide nanoparticles or other forms. Electrospinning is a very simple technique which involves a series pump with a polymer and the application of high voltage on the tip of a syringe, which injects with a specific rate the polymer. In this way, you can create fabrics, woven and non-woven, and it is really nice to create several polymeric-based materials. For example, you can see here that depending on the conditions you use, you can create this completely different composites and different topographies. Here they used polysulfone in order to create these fibers. But you can also use a wide range of polymers. In this case, for example, they used polystyrene and they create a completely different morphology. So depending on the injection rate, the applied voltage, the concentration of the precursor, etc., you can tune it and you can create different shapes. And we also have the layer by layer assembly method in order to create coatings. Here is the method is schematically shown here. So you use successive layers of different charged, let's say, things, and this interaction between positive and negative charged layers provides a thicker and really good coating. Here, for example, if we have cationic polyelectrolytes and anionic proteins, and we do successive layers of this, we will have the fabrication of a layered structure, which is a layer by layer assembly of different charged films. And you can either do it on particles. Here you can see that we start with the core, we go to the first layer, the second layer, the third layer, and so on and so forth. Or you can do it on a surface. So it is a very nice method to either coat surfaces or functionalize and coat particles or other objects. Here it is again used. I have mainly used examples about superhydrophobic surfaces because there are the surfaces, one type of the functional surfaces we'll talk in the second lecture next week. And here by doing layer by layer films, they developed a branch-like structure of aggregates you can see here. And depending on the deposition time, they found a plateau on the contact angle, so there was no need to increase the deposition rate from a step, let's say, from 300 seconds, since the contact angle remained the same. So up to now, I have quickly passed to the more commonly used methods of create an initial pattern on a surface, then use this pattern either to etch the material itself selectively or to deposit selectively a material. In this way, we can create whatever we want. I have shown you nanopillars, spots, thicker pillars, high aspect ratio pillars, low aspect ratio pillars. All these kind of topographies can be used in several techniques. In several applications. So, but how can we characterize all these topographies? I have already shown you images of microscopes, of scanning electron microscopes, showing very small objects. But here I'm trying to present you the most basic techniques used, let's say, for MEMS, which is mechanical systems, or functional surfaces. And of course, we will start with optical microscopy. Nowadays, we have very good lenses. We have different type of microscopes. We have stereoscopes, inverted microscopes, and by using very good lenses, we can go, let's say, up to 100 times or 200 times magnification. So we are able to see small objects, mainly on the micro scale. Of course, different type of microscopes have been also developed in order to observe different things. Here, I'm showing you a fluorescence microscope in which we can see cells, human cells, and how the core is painted differently from the outer part of the cell. We also have confocal microscopes in which we can focus on different depths of the sample and see what happens there. So different types of microscopes, because of the evolution in the lenses and in the analysis software, can provide quite good information up to the micrometer scale. For film thickness or crystallinity, we have ellipsometry and XRD, X-ray diffraction. In ellipsometry, we have an incident light, and then we have several polarized, let's say, lights that in which we use in order to calculate the thickness of the thin film that we have deposited. Whereas here, by the Bragg's law, we can define the distance and the crystallinity of the structures, of the powder, of solids, of liquid samples, and how the molecules are arranged. If we go to the morphology, as we saw before, we have scanning electron microscopes and transmission electron microscopes. The difference between these two types is that in SEM, we take a look in high magnification of the surface of the sample, whereas in the TEM, we look inside the sample. We can see what is the cross-section of the inner part of the sample. Of course, in order to see inside and in the inner part of the samples, the TEM sample preparation is quite laborious, and you have to find, to trim, let's say, the sample in a very small size, approximately some nanometers, in order the electrons to be able to pass, to transmit through the sample and see how it goes. Of course, both types are used. If we want to see the surface, we use SEM. If we want to see inside the sample, we use TEM. Other type of microscopies is the scanning tunneling microscope, in which we had a tunneling voltage and a tip, and if the sample was conductive, we could see features smaller than 0.1 nanometer. But the drawback of this method is that it was only able to characterize surfaces that were conductive. They couldn't be used, this couldn't be used on polymers. And for this reason, people invented the atomic force microscope to overcome this basic drawback, and can also probe polymers. The idea is quite simple. As the old gramophone worked and played music, we use again a small tip that passes through the topography in different modes, and by this interaction, we get this kind of profiles. The modern AFM microscopes can work on contact mode, so you have a mechanical interaction between the surface and the tip, and of course in non-contact mode, in which you have, when the tip is very small and very sensitive, when you go really close to the topography, you can see vibration, and this frequency of the vibration is translated to an image. And of course, this kind of microscopes have been also used to to measure friction of nanostructures like here, or to probe the adhesion of deposited layers on surfaces, etc., etc. So if we wanted to compare again all the, let's say, microscopy techniques, we would choose depending on what we want to see. If we want to see something with a very good resolution, I would go with the SEM, not an optical microscopy, but it is not necessary to use a TEM or STM. If the feature sizes are quite large, then SEM again is the best tool. But if you have nanoscale features, it is probably to go with AFM. And of course, it depends on what type of image you want to extract, if it is 2D, 3D, etc. And the last part of the characterization method is related to the chemical composition of the surface. So in a lot of applications, we apply a thin film, we have a specific surface, and we want to know the chemistry of the surface. One nice tool is Fourier transform infrared spectroscopy, in which we use a specific range of wavelength of in the light spectrum, and this mid-range infrared light causes vibrations, and these vibrations are different depending on the chemical structure you have. So we have specific chemical structures dedicated to specific energies and specific wavelengths. So by using this, you can understand what chemical structure you have on your surface. Of course, we have different types of FTIR, like the reflection mode, the specular reflection, the diffuse reflection, depending on what you want to measure. If it is a powder, if it is a solid, if it is a transparent solid, etc., etc. Here is a representative example of a spectrum. So you can see here that this peak is dedicated to hydrogen bonds. This is a double bond between carbon. This is CH2. This is CH. This is carbonyl, etc. So specific peaks are evidence of specific chemical structure inside your surface. And a more, let's say, exotic and very detailed method is the X-ray photoelectron spectroscopy, in which the photoelectric effect is used to identify the elements that exist inside the material. So when you have a specific electrons hitting the surface, depending on what you have on the surface, photo emission changes. And this change can provide you qualitative and quantitative data about the composition of your surface. So here I have two examples of graphs. Here you can see that we have focused using this method in fluorine, and you can see that the composition of the surface in CFX, CF2, CF3, and how much of each one do I have. And here, if we go to the carbon peaks, then again, we can find the different chemical structures, the chemical nature of our surface. So that is all for today. I try to provide an overview of really common techniques used in micro-mechanical systems and functional surfaces, and some basic characterization tools in order to be able to follow up to the next lectures that are dedicated to specific, let's say, application or specific methods that are used to collect or to clean or to extract water and reuse it. So thank you. That is all for today. Next lecture, as I said before, will be about functional surfaces and how these functional surfaces that are fabricated using these methods can be used in water-related applications. Sebastian, I will pause or stop the recording. Okay.
I think we can stop it now.
Yeah.
Thank you very much, Kosmas.